Section P5 is solving inequalities algebraically. First, for linear inequalities.
Okay, to solve a linear inequality, you can subtract your 3x from both sides, add your 7 to both sides, divide by 2, and x is greater than 8. And then remember on our number line, that since x cannot be equal to 8, we use the parenthesis on it and then shadow the greater than part. Now, if it were greater than or equal to 8, that's when we use the bracket.
Here's another example for linear inequalities.
Okay, to solve another linear inequality, I'm going to get rid of the fraction by multiplying both sides by 2. Okay, I'm going to subtract the 2 from both sides. Subtract the 2x from both sides. And now when I remember for our inequalities, when you divide or multiply by a negative, you have to flip the inequality sign over. So x is going to be less than or equal to 2. And then to put that on our graph. Okay, since it can be equal to this time, I am going to use the bracket and shadow the less than direction.
Now, how to solve a double inequality.
Okay, to solve a double inequality, it works the same way. It's just now we kind of have 3 sides that we have to keep everything balanced on. So I add one here, here, and over here. So we do it in all 3 places. Okay, now with our number line, okay, we're going to use the bracket on -3, a brace on 2/3, and we shadow in the middle. Kind of a little better.
Solving absolute value inequalities.
Okay, to solve absolute value inequalities, remember this inside here is less than 2. So I have 0, 2, I know we're coming out this way. But once you come out so far and come to like -3, this inside can no longer equal -3 because the absolute value of 3 is not less than 2. So that means our absolute value is not only less than 2, it's also has to be greater than -2. And now when we go to solve this problem, we have to add 5 to all 3 sides, and x is less than 7 and greater than 3. So up here on our number line, okay, 1, 2, 3, 4, 5. Try again, Mrs. Frank. Put 0 over here. 1, 2, 3, 4, 5, 6, 7. So x has to be in the middle of 3 and 7.
Investigating polynomial behavior. Okay, for this problem, we're going to take this polynomial and decide when the interval is negative and when the interval is always positive. So we're going to start by setting the polynomial equal to 0, and we can factor it into x minus 3, x plus 2. So the solutions are 3 and negative 2. So when we go to draw our parabola, put the 3 and negative 2, and then we can see that the interval is negative for the x values from here to here, and the interval is positive for these x ranges. Okay, so the intervals of when that equation is negative, that's from here to here, that's between negative 2 and 3. And the intervals for when the polynomial is positive, that's these y values from here to here. So this goes out to infinity. So that interval starts at negative infinity and ends here at negative 2. And then it has a second interval this way that starts at 3 and goes to positive infinity. So those are my two positive intervals. How do we solve a polynomial inequality? Okay, to solve a polynomial inequality, we first have to set the inequality to 0. And then we can factor it. And we find the solution set of negative 4 and 3/2. So when we go to graph our parabola, once again, we can find the solution intervals for when the polynomial is greater than 0. So the y values are greater than 0 in this x value range, and it's greater than 0 in these x value ranges. So that leaves our solution set from negative infinity, not 8, from negative infinity to negative 4, and 3/2 to positive infinity. And since the solution is both of those, I really should put the union symbol between the two. Unusual solution sets. Okay, for an unusual solution set for this polynomial set greater than 0, if we try to factor it, we do not have two factors there that will multiply to give us 4 and add to give us 2. So we can find the vertex by plugging in negative b over 2a and find out the x value is negative 1 and the y value is 3. So I know the vertex is at negative 1, 3. And we have a parabola. And you can see from the parabola that all of our values for x, y is in the positive range. So that means the solution set for this problem is all real numbers. So it goes from negative infinity to infinity. For this problem, for the polynomial to be less than or equal to 0, we can factor the polynomial and find out that x is equal to negative 1. So we have a parabola. Come on, Ben. There we go. We have a parabola that just touches the x-axis at one point at negative 1. So when this polynomial is less than or equal to 0, it's not an interval. It's only at this one point where it equals 0. So my interval is just x equals negative 1. Another unusual set. The solution set for this polynomial being less than 0, the graph is over here in the green, and you can see for the solution set that the graph is never less than 0. So the solution set is the empty set. Unusual solution set number 4. Now the solution set for when this polynomial is greater than 0 is actually everything except right at the vertex where x equals 2. So everywhere else on this graph, y is greater than 0 except that one point. So its solution set is actually negative infinity to 2 with the union of 2 to negative infinity. That way we leave out the x equals 2. We did it. We finished the video on solving inequalities algebraically. Yay! Now we get to do our problems out of the book.